Hello, and welcome back to part 3 of my series on programming PLCs. Today we are going to be looking at integrating PIDs with your PLC logic, as well as integrating POUs specifically for programming scaling functions. So without further ado, let's jump right into it. Okay, so the first thing we're going to do is we're going to open up Factory IO, and we are going to open up a scene. We're going to jump into level control scene down here. And that's going to give us a nice big tank of water with a fill valve up here and a discharge valve down here. We can control this. Let me dock all the tags here. We see we have a discharge valve, a fill valve, flow meter, level meter, all sorts of fun stuff. We have these PV and SP, which are our little displays down here. That's going to display our set point and our current value. This big this big scale here is the level meter that reads a voltage depending on how high in the tank the water is. And if we want to take a quick look at that, let's open up the fill valve here. Press play, and that is going to fill that up. We can see the level meter is starting to gain some voltage here. So everything that we're working with goes from 0 to 10 volts. It's a quick introduction to the system. We're going to skip the buttons. I'm going to challenge myself to do this video a bit quicker than last time. The last one was coming out just north of 40 minutes, so we're going to try and shorten this one down. We will jump into CodeSys. Okay, so we are going to go ahead and start a new project. We're going to go ahead and open one up now. We're going to go standard project, and let's call this one PID, because that's what we're going to be focusing on, is the PID control. We're going to go for ladder logic diagram again. I keep saying this, but make sure you do not choose ladder diagram. We want ladder logic diagram for the full functionality here. And we are going to open this up. All right, so we got our empty program here. Let's start by putting in a few variables. So obviously we are going to need a fill valve. That is not going to be Boolean. This is going to be a real number. So real numbers, they can handle positive, negative, decimal points to quite a lot of decimal points actually. So we're going to make those a real value. A fill valve, and we're going to have a drain valve as well. Real values, both of those. We need a level meter for our level meter, obviously. We have our set point potentiometer. That was this little dial right here. That's our set point potentiometer. So we're going to use that to set the height of the water that we want to have in the tank. Set point potentiometer there. We're going to skip over the buttons just so we can just jump right into it. This is not going to be a real simulation, and we're not going to have the e-stop in there. This is just going to be for the sake of getting the PID programmed. Let's expand that a little bit. I do want to get in some variables for our PID. If you're familiar with PIDs, what they do is they measure the error between your desired system state and the current system state. So if we say we want 150 centimeters of water in the tank and we have 0, that's going to say, oh, we got a 150 centimeter difference. And it's going to apply a correction to that. So we can give it some load, some coil, which in our case is going to be the fill and the drain valves. And we are going to use those to correct that value. So it's going to listen for the current state, compare it against the desired state, and then apply a correction via our loads. We need a couple variables for this. So if you're familiar with PIDs, you know that we need 3 values. We need a proportional number. That's going to be KP. Typically, the proportional number is represented as K. There's an integral. In this case, is time measured. That is that's the amount of time that the PID is going to measure to get an integral of. This helps with the reaction speed of the PID. And we need a differential. Let's call that diff. And the differential is going to take the derivative of the function based on a certain measurement time, and that's going to help correct for the slope, give us a nice approach angle into our desired value. Uh, we're trying to we're trying to avoid overshooting, oscillations. We want to keep the steady state error relatively low, but we are going to have some. This water tank is fairly tricky because it sloshes around. It's a physics simulated environment, so this water gets sloshing, and if you have oscillations in your system, it's going to just oscillate out of control. So we're going to have this be a pretty damped system. It's either going to be critically damped or over damped, one of the two. But we need to avoid those oscillations at all costs. Otherwise, we're going to be oscillating forever. We're going to put in a couple more just because, again, I'm working off of a pre-solved. I've solved this scene already, at least to my liking. We are going to need a scaled level, scaled potentiometer, and these are all real values. Anything else I'm missing here? I think we are. Oh, we need the unscaled level and the unscaled potentiometer. Unscaled level. And we want an unscaled potentiometer. And this is going to relate to the fact that we have to scale our inputs and our outputs. So we know we want 150 centimeters of water, let's say, but that's going to read that as 5 volts because that's halfway up the sensor. So these we're going to have to convert these values from voltages from 0 to 10 volts and scale them to match our actual values, so that an operator could look at this and understand what's happening. If you had the tank, at 100 centimeters of water and it was saying something like 3 point whatever, that wouldn't make any sense to someone trying to fill the tank. So we're gonna scale these and make them usable values. First thing we're gonna add in, let's go ahead and add in our PID. So the PIDs in COSYS are kind of hidden. Let us just try this. We're gonna put in a box. And can we find? We cannot find it yet. These oh, these names are so short. This is hidden in a library here. So we're gonna have to go and manage our libraries real quick. We're gonna jump in here to Library Manager. We're gonna add a library. I believe it's an application common util. That's the one. We're gonna add in the utility library. Simple as that. So we just went to Library Manager here, added the library, added the utilities library. I believe that's the one that has the PID. We're gonna add our block now. We are going to add a box with enable and output. So that's going to give us the it's going to ensure that our PID stays on. There we go. So this switch would enable the PID. We're going to delete that switch. It's always on. Just to make perfectly sure. I like to see these branches to make sure that things are going to work. And we're going to start plugging some stuff in. So just follow along with me. So scaled level. Scaled level is not a variable. This is the scaled level. Scaled level. There we go. Make sure I didn't add that somewhere. I'll delete this PID. Don't need junk cluttering everything up. Okay, so we got our scaled level in there. So that's going to be our actual value. The PID is going to read this. It's going to say 0 to 300 because that's what the range is on our sensor. And then it's going to compare that against what we desire, which is going to be our set point. So that's going to be scaled potentiometer. I should make my names shorter so I don't have to go through so many typos. KP, that's obviously going to be KP. TN, this is the time measured. This is our integral component. How long it is taking that integral over. And TV is our differential, so it's our derivative. If Y manual, Y offset, we can set those both to 0. We're not doing any offsetting here. But now we need to set our Y min and our Y max. So that's going to be how high the output can go, both in min and max directions. We actually have two controls that we're going to be controlling our PID with. We have two different ways for it to adjust its value, which is our fill valve and our drainage valve. So what we need to do is remember that we're going to have a valve working in the opposite direction of our fill valve. We're going to have a -10 for our min and a +10 for our max. That's going to allow us to use both valves, and we'll get to that in a little bit. But that's going to allow us to use both valves to fill and drain to make sure we end up at the right level. Um, don't think we need manual or reset. We're going straight through this. If you wanted to bypass the PID, you could set a manual input, and you could also set a reset as well. But we won't be doing that today. Now we're actually going to make a new variable here. We're going to make this PID out. This is going to give us. This is not a PID variable. This is a real number, but this is going to give us the number that this is going to give us the number that PID is going to output. So we're going to take this variable and we're going to be able to move it around and scale it and have a different logic apply to it. But this is going to be our output. It's a number ranging from -10 to 10. Limits active. We're just gonna ignore the limits, ignore the overflow. The overflow is if there is an error that overflow will trip. We're gonna ignore that for now. Like I said, we're gonna get through this one quickly. This is not gonna be a 40-minute video. Okay, so the next line of logic that we need to incorporate. I said the next one, not the one before it. Okay, is a little bit of logic about how it's going to handle these values, what it's going to do, because we need to get this PID out value to our fill valve and to our drain valve. So what we're going to do is we're going to do some math operators because we want our positive values. This is how I set it up. I want my positive values to control the fill valve, and I want my negative values to control the drain valve. So if PID out is greater than 0, then we are going to move. Where's our move command here? You're going to move the value of PID out to fill valve. So, the typos. We're going to just use this fill valve. Got it? So if the PID value is out, if it wants to increase the value of the measured level here, it's going to pump out a value between 0 and 10, and then that's going to move the PID out value to the fill valve. Pretty simple. We're going to do the same thing again, except we're going to change this to a less than operator. You see that switch there just by me changing the names. If it is less than 0, it is going to move the PID out value to fill valve. The problem with this is that it's going to move a negative value, and we're only dealing with 0 to 10 volts. So we need to convert this value to a positive number. And how do we do that? We just grab the multiply block. So we're going to PID out by -1. And then we're going to put that to the drain valve. Usually put underscores, but I didn't today. So it's tripping me up a little bit. And just to make sure that we don't have both valves open at the same time, we're going to add one more constraint. So we have these two lines of logic. If the value is greater than 0, it's going to continue along this branch, and it's going to move that value to the fill valve. We're also going to make sure that the drain valve is off. We're going to do that by moving 0 to the drain valve. And if you guessed that we were just going to copy this and put it on the end here and change it to the fill valve, you'd be absolutely right. So this is just going to ensure that when the fill valve is being activated, the drain valve is not being activated. And vice versa, when the drain valve is being activated, the fill valve will not be activated. Gotta fix this. Drain valve and fill valve. So this is just making sure that no stored value is going to be held and it's going to continue to drain or something of that effect. I don't know if it would work well or not, but I want to see that these are definitely closed when it's going in the opposite direction. And for our last line of this logic, before we get into the scaling functions, is we want to have a little bit of a dead zone because it's very sensitive. The water sloshes, and just the water sloshing will cause it to want to correct the value, whereas we know that the water can just settle, and it will probably be at the right value, but it's going to want to keep making corrections, and that's how you get these oscillations. So we're going to add a deadband here. So what we're going to do is we're going to take the difference. We're going to take the difference of the scaled level. So that is, again, I always do it with the underscore, but not today. So I brought this on myself. If the difference between these two is less than some value, we're going to call that our delta. Yeah, we'll initialize this. It's a real number. Less than 2. It's less than 2 seems like a good spot to start. Here, I'm going to just punch this in. We got this 2 here. So if the difference between the level and the set point is less than 2 centimeters, we're going to call that good. We're just going to have a deadband there. But we could have it be, between 0 and -2, and that would not apply to this logic. So what we need to do is take the absolute value. You can just do it right like this. If the absolute value of our delta variable is less than 2, then we're good. And if that is the case, how do we shut off both of these fill valves and the drain valves? We just copy this over to here. Copy this over to here. So let's review our logic here. We have a variable for our gain, our proportional gain. We have a variable for the time measured for the integral component, and we have a variable for the differential component. We then have some logic that controls the where the signal is being sent to based on the PID value. If the PID value is greater than 0, it's going to the fill valve. There it is, the fill valve, and it's turning off the drain valve. And if the PID value is less than 0, it is going to multiply that by -1 to get that to a positive voltage. Good. And then it's going to open the drain valve that amount, and it's going to shut off the fill valve. Then, when we are close to our value, it's going to check that based on the scaled level and the scaled potentiometer. It's going to take the difference between those two. Actually, just like this. See, this is our error up here, and now we're just referencing that error again down here. That's going to give us this value delta. And if the absolute value of the difference between our set point and our current point are less than 2, then it's going to shut everything off. That's going to help us out with the crazy oscillations you get from this kind of setup. So that's it for the PID control. Now what we need to do is actually scale our values. And for scaling our values, we are going to make a POU, personal organizational unit, I think it's called. Listen, I'm not an absolute expert on PLC programming, but I've learned a bit. I want to demonstrate what I've learned, and I want to teach you how to do it at least as good as I know how to do it now. Add object POU. There we go. Click on application. And we are going to make a new function. It's going to return a real value because these are going to be our values from 0 to 300. Okay, so we are going to make this POU now. This POU, this special function block that we are going to make, is going to be for the scaling function. The scaling function, I'll put up a formula on the screen. Is right there, but it's essentially our input. So we have our input range from 0 to 10. We have our output range from 0 to 300. We take our input, multiply it by the difference between the outputs. So in our case, the difference is 300 divided by the difference in inputs, so that is 10, so 10 minus 0, and we add the minimum output value to place that value that we've just got in the scale. So it's going to look something like this when we get to our variables. We are going to need our input. These are going to be real numbers. Let's give me the real variables. We're going to need the input min, the input max, the output min, the output max, and we're gonna need some variables to kind of help us out here, but we'll just make those as we go because we want to be able to transfer these math operations to variables and then use the variables to go to the next math operation because this all has to be done one at a time. So first thing we're going to do is we are going to find how far up on the scale we are, and we do that by taking our input and subtracting it from the input min. In our case, our input is just going to be whatever the input is because input min is 0. But let's store that in variable 1. And then we are going to let's also get our other subtraction here. That is going to be our input max and our input min. This is giving us the full range of the inputs. And we're going to put that to variable 2. So we have our difference of our input from our input min and our input max from our input min. So we got 2 of those variables. That's our inputs. Let's make a new line. Boom. And we're going to do the same thing. We're going to get ourselves a output max minus the output min. Now this could all be really shortened down because our minimum for all of this is 0. We could really just be plugging in some variables here, but this is versatile. You can use this in other programs. We got our variable 3 there, and we're going to do a little bit of division. So we have all of the variables we need for the division. We are just going to divide our variable 1 by our variable 2. And that is going to variable 4. And now for our last line, we are going to multiply. We're going to multiply our variable 3 by our variable 4. And finally, that gives us our variable 5. Our variable 5 now, variable 5, is going to be added to our output min. Variable 5, output min. And that's going to give us scaled out. That's our scaled output. All right, so if we go back and click back into our main program here, we should be able to pull up a POU. Let's start a new line. And we're going to plug this POU in here. Let's see what happens. We got no inputs. We got no outputs. We should have a bunch of little bars here that allow us to output stuff. So let's take a look at our POU again. We look at these variables. None of them are assigned to an input or an output. So let's go ahead and do that. We want to put in all of our input variables. So we're going to input what our mins and maxes are. Those are all inputs. We're only going to have one output really. So all of these go to input, 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 input. These are hidden. We don't want them showing up on the block. That's all calculated within this function block. And then this is going to be our output here. I'm going to build that function block. There we go. We have some numbers. Beauty. We don't need a switch to turn on our scale, so our input is going to be, well, we're going to have to do this for all of our inputs. So let's make this the fill valve. And our input min is 0. We know our output max is 10. Our output, did I say fill valve? No, that's not true. I'm sorry. What this is actually going to be for is, all right, so let's put in our POU. We're going to put that in here. Don't need this switch. And our input here, we're trying to scale a couple things here. We're trying to scale our level meter or height meter, and we're also trying to scale our potentiometer. We want to scale our output so that we can read 0 to 300. We want to scale the tank level so that that also reads 0 to 300. But we know our inputs are 0 to 10 volts. Where are we? Where are we here? We want our scaled level. Scaled. Nope. This is unscaled. Unscaled. Unscaled goes in. Unscaled goes in. And the scaled comes out. Isn't that right? This is going to be 0. This is going to be 10. We're going to have 0 here. We're going to have a 3. Oh, come on. Kick me out. Hold on a second. Output shouldn't be in there. Let's go back and fix this. Output should not be in there. Actually, we didn't even reference output, so was not needed. But let's rebuild this. I'm only human. I make mistakes. Crap. Our input is going to be scale or unscaled. Unscaled potentiometer. Input min is 0. Input max is 10. Output min is 0. Output max is 300. And then we should get a scaled out value, which is going to be our scaled potentiometer. Not quite sure what you are, buddy. Let's have a look. What are you? Only one output. Anyways, I don't know what that is. That might just be like a placeholder. But our scaled output is our scaled potentiometer. Let's plug in another POU. Input again is going to be, input is going to be our unscaled level. And our input min is going to be 0. Input max is going to be 10. Output min is going to be 0, and the output max is going to be 300 once again. Remember, these are matching. We're trying to match the potentiometer to the level. And our scaled out is going to be scaled level. Scaled level. Let me reference the charts. I think we are all good here. I think we have everything we need to actually plug this in. Get out of here. Question marks. I know what I'm doing. Oh, don't forget, we need to now that we've done all the fun stuff, we need to go in here and scan our network. So down to your tool tray, start your PLC, just like we showed in the last videos. I said start the PLC, thank you. That's right, before we get right into it, we're gonna scan this network here, get our device. I'm gonna show you one more thing. Oh, I hope this isn't another 40-minute video. Scan the network. We got the device. Perfect. We are going to add. Okay, so you're going to go up to application here and add an object, and you're going to come down to visualization. I've already added mine in. Click on the visualization tab, and you'll have a toolbar on the side just like this. We want to go into special controls here, and we are going to add a trace because we want to see what's going on graphically. Now we're going to configure this. We're going to configure the trace. We don't need a trigger for this. We'll just have it running. Ask. There we go. We're gonna add a variable. This variable is going to be from our application, and that variable will be our scaled potentiometer. This should be on the y-axis. Good. And we're going to add another variable. This one is going to be our scaled level. I'm used to seeing these PID controls with green as the set point, so I'm going to set that to green. And I'm going to set this one to blue here. And that should be good. So to set the scale in the X and Y, we're going to go to the visualization trace up here. Make sure that it's pulling the data from the main task. And we're going to go to display settings. Very simple. I just missed it. Give that, let's say 20 seconds. Have a little bit longer. We'll go for 30. We'll go for 30. Okay. Now we want to fix the y-axis. Fix from 0 to 300. And this should be all good. So we have something that we can visualize graphically how the PID is actually performing. So with everything else set up, we can go ahead and click play, and we're gonna. Okay, and before we go into factory IO to get this all set up, we have our visualization, we have our program, We need to make sure we don't forget to add in our symbol configuration list to pass all these variables along to factory IO. So we are going to go into here. We got to build our program first. Building, there we go. Select all of those. I don't believe we need to pass along our POU that's handled internally by the PLC. All right, so we got our symbols. Build it one more time for good luck, and let's log in. Let's check on factory IO here. We're going to go in and configure our OPC client. So we got the right server. Oh, hello. This is what happens with visualization. It brings up your window. There we go. I think there's a way to turn that off. But anyways, we got our PRG variables. Okay, so some stuff in here is not what I put in. So to make sure, you can see that these variables, I did not type those in. So let's go back in here and we'll set this limit higher. Let's say 75. We'll just make sure we're pulling all of the variables. Yeah, you can see there's some more down there. We were missing some. Let's go ahead and start plugging things in. Where do we want our flow meter? We didn't set up the flow meter. We just want the level meter. Level meter's right there. Plug that in. Didn't set up the reset. We did set up the set point though. It's actually going to be way down here. This is one of these default. This is one of these default variables that's hidden in CodeSys. We want our set point to be the scaled potentiometer because that's going to be our 0 to 300 value that we set physically. Anything else? We got those two inputs. I think those are the only two inputs we need. We need our discharge valve, which is our drain valve here. Fill valve. It's got this little exclamation mark because I had that as a forced value before. So we're going to unforce that. Our PV, that's our present value. I don't know if that's what it actually stands for, but that's what we're going to call it today. Our present value is... Where are we? This is actually going to be down here. Level meter. Scaled level. That's what that is going to... No, I was right. Level meter goes up here. PV is our... give me that. PV is our scaled level. It's our scaled level. Set point. Scaled potentiometer. Discharge valve, fill valve, PV, SP. We didn't use the rest of these, so that should be okay. Let's give it a try. Where are you going? Where are you going? I know what's going on. What is happening here is that we did not set any of our values for... The problem is that we didn't set any of our values for the actual PID controller. So you can see here, everything's just set to 0. We're going to have to change those. Let's maximize this. Let's pick some preliminary values. We're going to have to dial this in. I think all we need is a KP value, and we need it to measure some amount of time. So we can set this really high, let's say 1,000, and just see how it does with that. So we've updated those live. This should be 0. So we're not getting a read on our scaled level or our scaled potentiometer. So why is that? Why are we getting no read? Oh. Oh. I still force this. Let's see now. Ah. You see this? We're getting a reading of 10 here. That odd behavior is definitely coming from the time measured value. So I just set that to 0.1. But we are getting an unscaled value on our display. So let's have a look. Fill valve is freaking out here. Scaled level, scaled potentiometer. That should be good. It should be, but it's not. Why is that? Okay, that's what it was. We got a little mixed up there. So we're reading correctly now. Reading correctly now. Not reading anything on the level meter. So the level meter must be one of these guys. Give me a moment, I'll figure it out, and we'll pop right back in. Okay, and we have it all resolved here. So, you'll have a look. Right now, what we're doing here is we were multiplying PID out by -1 and sending that to drain valve. And then right after that, we were sending PID out again to the drain valve. So it was giving it a negative voltage after all that hard work. So you can just delete that that move PID out to drain valve. Just delete that, and you'll be okay. The other thing that I had to fix, going into our connections here, you should have something like this. Level meter is unscaled level. Set point is unscaled potentiometer. And then our outputs, where it's going to display to, is to the scaled level and the scaled potentiometer. And then we have our discharge and our fill valve up here. That should get everything fixed up. And now we're off to the races. So let's see how our current values are working out. Let's see how our current values are working out. Currently, our KP is 1 and our time measured is 1. We have a dead band of 2 centimeters. We're within 1 centimeter here. So that's all looking really good. Let's try a different value. Let's bring this up. We got 260 there. Let's see if this hits 260. Oh, that overshot quite a bit. Oh, then it settled down. Hey, that's pretty good. We're within 1 centimeter. Let's go ahead and get a visualization on that. I just went down to our visualization here, and we have our graph. So let's try a different value. Let's go back down to 123. 123 centimeters in the tank. That is fantastic. That is fantastic. And so we are currently, so this is our visualization here. That goes straight to the value. That is wonderful. We go over here, back to our program. We don't actually have any differential value here. We don't have any derivative value. I think I've been interchanging the word differential and derivative value this whole video, but it is late. I've had a long day, so forgive me for that. But that's looking good. So we have our gain is set to 1, the integral value is set to 1, and we're getting very good behavior from this. Let's see if we can set it somewhere close by, and we'll try and trick it. So it's going to overshoot a little bit. We're oscillating pretty bad here. You can see it. You can see that it's oscillating. So there is some risk of oscillation. And we could spend time to tune that out. We'll give it the old college effort before we end this video. You can spend some time. I have a set of values that works that I can just go ahead and plug in. But really, you can spend quite a long time tuning these PIDs. They're finicky systems, especially when you're dealing with this. Look at that. You can adjust things like your deadband value, which we have set to 2. Where's our deadband over here? Our deadband was right there. You can update your PID values live with these prepared values here. If you wanted, you could probably even add some more dials that you could set your PID values within factory IO. That would be kind of cool. Let's hit reset on that. The values I have that worked, I'll go ahead and plug those in for demonstration. Typically, when you're tuning PIDs, what you would do though is you would start with 0 integral and 0 derivative, and you would just start with your K value. There's a whole process for PLC tuning. I think I'll maybe link that rather than making this video any longer. Let's go with our previous values that I have to find again. Have them written down. All right. KP was 1. Time measured was 5 seconds. And derivative was very low. Plug that in. And you see it settled that down right away. Settled that down right away. It's going to go straight to 0. Well, hopefully it hits 0. It might actually stop at 2 or 1 because we have that deadband there. In hindsight, we probably should have made that deadband a variable itself. That 2. So if you wanted to do that and you wanted to tune your PID really precise, so yeah, we can see that the delta here is about 1.8. If you wanted to tune this deadband right now, because I have it hard coded in, I actually have to stop the PLC to change that. Well, let's go. Let's give it a quick shot. I know the video's getting long. Deadband. Deadband is a real number. All right, so now when we log back in, we can update our deadband value live. Currently, it's set to 0. Let's see how it behaves with 0 deadband. So far, so good. And let's visualize this. Let's go over to the visualization tab. It's approaching our set point, slowing down. Oh yeah, that's going nice and slow. We're at 110. 111. Ooh, that is fantastic. What's it going to do now, though? Oh, we're starting to get some oscillations here. We've got this steady state error. So you see that's getting worse and worse. It's got steady state error and it's starting to resonate. So let's set our deadband. Let's set a value of 1. Let's try that. That'd be twice as tight of a tolerance as the 2 was. So let's try and pull it out of this oscillation. We can. Ooh, it's going. This would be a good time to have a stop or a reset or something plugged in, and you can just bypass the PID and stop this from happening. But we are just trying to control the PID today. Okay. Broke it. All right, let's try. We got a 1 centimeter deadband. Targeting 91 centimeters. We're slowing down. Ooh, we're oscillating a bit. But it should start cutting out now that it's within the deadband range. Let's set that back to 2. Let's set that back to 2 and call it a day. It's been a... Oh! I didn't actually pass the value. There we go. I didn't actually pass the deadband value. Let's give this a quick try. Give this a quick try, and I promise we're calling the video done. It did 27 all right. That did 27 pretty well. It damped itself out. Very good. All right, we're racing up to the finish line. We're going to start to slow down to prevent that overshoot. Getting some oscillations here, and that works. And last thing we're going to try is we're going to drop the value down because its behavior in the positive and negative directions is actually quite different. The drainage valve has a much higher flow rate than the fill valve, so it'll give you different behavior. Oh, beautiful, beautiful, and there you have it, folks. It was the challenge. The PID is, there's a lot of setup to it. You have to scale your values. It involves a lot of variables. Um, but once you get it plugged in, it's as simple as just figure out a good gain value, and then you start tuning your integral and your derivative. Um, there are guides for tuning PIDs. I highly suggest you check them out. And for this PID that I've made today, especially with the setting up a POU, that there's a video that helped me out a lot. I don't remember the name of it right now, but if I remember that, I will post that link in the comments. I don't know if I'm allowed to post links yet, but I will do my best to find that video and get that put up for you. So until the next time, this has been Will, and enjoy your new PID controlled tank. Thank you. Bye.